Hey everybody, welcome back to physics. I hope everyone's doing well. Today we're going to start a discussion of optics. Optics is a kind of a special case of our discussion of waves. So far we've discussed waves in general, but optics is the study of the wave nature of light. How light works in a lot of different circumstances. We're going to be trying to answer some questions about light, what light is. You've experienced light your whole life, but light is profoundly mysterious. If someone asked you, what is light? And how does light work? It's kind of tough to answer that question. And we're going to try to answer that question today in this video. So here are some questions that we will explore in our study of optics. Again, this is a special case of our study of waves. We're still within our discussion of waves, but now we're focusing particularly on light. So here are some questions. What is light at the most fundamental level? How do we know light is a transverse wave? Why are sunglasses polarized? And what does polarized even mean? We're not going to answer every single one of these questions in this video, but we'll start our discussion of light and what light is doing all over the universe. How do mirrors work? What do you and a mirror have in common? Why are materials different colors? How do eyeglasses work? What do glasses do to light to make people see better? And why do straws look bent and distorted when looked at through a glass of water? All of these questions and more will be explored in our study of optics. So to start off our discussion of light and optics, we want to discuss what light truly is. There's a few different ways that we could model light in our universe, and a few scientists a long time ago, 1800s or so, proved that light can be modeled as an electromagnetic wave, something we've discussed. Now this diagram is pretty cool because this diagram organizes all of the different light, all of the different electromagnetic waves that we can find in our universe. Now this diagram is a lot to unpack, so we're going to take it one little step at a time, see what kind of observations we can make with this diagram, and we're going to talk about what each one of these different categories of light truly are. Okay. So this diagram can be found in your reference table. If you open up your reference table, you'll find the electromagnetic spectrum, and this spectrum is organized where we have really long wavelengths and low frequencies here on the right. And then as we move left, we get smaller wavelengths, as you can see from the orders of magnitude here on the top. Smaller wavelengths on the left, higher frequencies on the left. You guys know that wavelength and frequency are related because of that equation V equals F lambda. As we decrease our wavelength, we're going to increase our frequency as long as the speed is held constant. Okay. So over here on the left, you'll find things like the long radio waves, TV, FM waves, AM waves, microwaves, infrared radiation. Here in this little sliver is our visible spectrum. Then we have ultraviolet, X-rays, and gamma rays. We're going to come back to this diagram, but let's see what kind of observations we can make from this diagram, just taking a look at it. Okay. So like I said, all types of electromagnetic waves have a corresponding wavelength, which is labeled at the top, and frequency, which is labeled at the bottom. It's important to note that if a wave has a higher frequency, it has a lower wavelength, and vice versa. It's something I was just talking about. Now, something that's really interesting with electromagnetic waves, and something different from sound and other like mechanical waves, is the energy of an electromagnetic wave is directly related to the frequency. The frequency of the wave, it tells us how much energy that wave is carrying. We learned with sound and other mechanical waves that the energy of that wave was directly related to the amplitude of the wave. How tall the crests were, how low the troughs were, told us about the energy. That's not the case with electromagnetic waves. Electromagnetic waves, the energy is directly related to the frequency of the wave. That's something that's not super intuitive, and it's kind of one of the weird aspects about physics. And we'll be talking about this a little bit more in a future lesson. But the energy of an electromagnetic wave has to do with the frequency. That means that as we get higher and higher frequencies, smaller wavelengths, that's the higher energy and thus more dangerous forms of light in our universe. Okay. So we live in the visible portion of the spectrum. What I mean by we live here is everything you've ever seen is in this tiny little sliver here. There's a lot of other light in the universe that we don't see, but everything you've ever seen, everything you ever will see lives in this visible spectrum of light. Here we have our red, orange, yellow, green, blues, and violets, and everything in between. Now, in this visible spectrum lives your favorite book, your favorite people, the visions of your favorite people, flowers, everything that we see in our universe, what we biologically are able to interpret with our eyes is inside of this visible spectrum, which is only a very tiny portion of this electromagnetic spectrum. Outside of the spectrum, electromagnetic waves and light does exist, but we can't see it with our eyes. We can observe things out in the universe like other types of galaxies, cosmic events, sometimes live in this other portion of the electromagnetic spectrum, which we can observe with various scientific instruments. But everything that we will biologically see is here in this visible spectrum. Okay, so what I want to do is I want to go through each one of these different types of electromagnetic waves, what we use them for, and how they affect us. Okay, so let's start with the radio waves. Now here on the right portion of our diagram is the, again, longest wavelength, lowest frequency, and thus lowest energy form of electromagnetic radiation. That's our radio waves. Okay. Now radio waves can have wavelengths as long as city blocks and very low frequencies. Radio waves are quite literally what we tune our car radios to. Certain frequencies carry the information from our favorite radio stations to our car. What's really cool about radio waves, something to think about, is the very first radio broadcast happened in 1906 in Massachusetts. That was the first one for entertainment purposes. And radio waves are very good at piercing our atmosphere, which means that those radio waves went out into outer space. We know that all electromagnetic waves travel at the speed of light, which we'll be seeing in a future slide. The speed of light. So if the first radio station was played for entertainment purposes back in 1906, and light travels at the speed of light, a light year is a measure of distance, and that's the amount of distance that light travels in 1 year. So 1906, we're in 2020, so we're looking at what, 114 light years from Earth is the very first radio broadcast. And that's absolutely true. If we go 114 light years away from Earth, you will detect the very first radio broadcast. Now, if there's any intelligent life 114 light years away from Earth, they are just starting to hear the very first radio broadcast that Earth ever created. We're always sending these radio waves out into our universe. Pretty interesting to think about. Here lives our AM radio and FM radio. AM radio means amplitude modulation. That's what that stands for. So that really fuzzy AM radio station, we're modulating the amplitude in order to transmit the information for the radio, where FM is we're modulating the frequency in order to transmit the information over those radio waves. Now, radio waves are very low frequency, low energy, so they don't biologically affect us at all. What's really cool about understanding the electromagnetic spectrum, it helps us kind of pick apart some pseudoscience that could be floating around our news. I'm sure you heard, but people talk about the fact that cell phone signals could affect our biological tissue. Things like the 5G towers causing all kinds of havoc in our world. All of that lives here in our low energy electromagnetic radiation. There's no evidence that this low energy radiation affects us biologically at all. So always be skeptical what the news media or conspiracy YouTube channels are telling us. Okay, so that's our radio waves. As we move to the left, we're getting higher energy, shorter wavelength, higher frequency. That's where our microwave radiation lives. Microwaves are the radiation that is in your microwave oven in your kitchen. Microwaves are pretty cool because at this range of frequency, we can actually affect water molecules inside of our food. That's how our microwave ovens work. You put your food in the microwave, you hit the button, and the microwave radiation is sent to your food. And as that microwave radiation is sent to your food, those water molecules start to actually resonate. They rock back and forth. And we know that if we're moving the molecules inside of our food, the motion of the molecules is directly related to how hot, the temperature of our food. So by rocking those water molecules and bumping into all the different molecules inside of our food, increasing the average motion, we're heating up our food using this microwave radiation. I'm sure your parents have told you, don't stand in front of the microwave. It's not good for you. But microwaves are such an interesting feat of human engineering. Microwaves are inside of something called a Faraday cage. So those electromagnetic radiation cannot escape the microwave oven. And that grate on the front of your microwave oven, those little holes that you see, they're created in just the way that the microwaves cannot escape your microwave oven. So feel free to look at your popcorn as it pops. That's totally safe for us to do. So next is our infrared radiation. Infrared quite literally translates to below red. Infrared we detect as heat in our universe. That's one of the ways that heat is transferred through radiation, and that's through infrared radiation. It's pretty interesting how infrared was discovered. A scientist was trying to figure out which color of visible light heated things up the most, and they actually had a thermometer below red as a control in order to figure out, in order to compare the temperatures of the other colors of light. And that thermometer that was sitting over here actually ended up increasing the most, the quote-unquote control. So even before our high-tech scientific instruments, we used scientific experiments in order to discover this electromagnetic radiation of infrared. And next, beyond infrared, we are now in our visible spectrum. This is where our reds, orange, yellows, greens, blues, and violets lives. And the difference between these different colors of light have to do with their wavelength and frequency. Red exists between 3.84 times 10 to the 14th hertz and 4.82 times 10 to the 14th hertz. Once we cross this boundary, we start getting into orange. And then once we cross the next boundary of frequency, we get into yellow, and then green, and then blue, and then violet. Violet has the highest frequency and the smallest wavelength and carries the most energy of all the light within our visible spectrum. And red carries the least amount of energy inside of our visible spectrum. So next we get to ultraviolet light. Ultraviolet literally translates to above violet. This is the type of electromagnetic radiation where we're outside of the visible spectrum. We can't see it anymore, but it does have some effects on our body. Once we pass the visible spectrum, we start reaching electromagnetic waves that do have effects on our bodies. Ultraviolet light is the type of radiation that actually burns your skin when you go to the beach. There's 3 different types of ultraviolet radiation: UVA, UVB, and UVC. That all exists here. UVB and UVC is related to things like skin cancer. At this point, the wavelengths are small enough to pierce our cells and start affecting the molecular DNA structure inside of our, like the nuclei of our cells. And once we start affecting the DNA, that's when things like cancer start developing. And that all is here in this ultraviolet spectrum. Notice that this is far away from all of those cell phone radiations and the microwave radiations that people tend to be freaked out about. Now, ultraviolet starts to get scary, but we do use ultraviolet for some important things like killing bacteria cells. We could use UV. There's actually some preliminary studies that ultraviolet can be used to disinfect surfaces for things like COVID-19. So past ultraviolet, we start getting into the X-ray portion of our electromagnetic spectrum. The name X-ray comes from the fact that when we first discovered X-ray radiation, we didn't know what it was or how it worked. We didn't have this whole organized electromagnetic spectrum. So because we didn't understand this portion, like this type of radiation, we used the letter X to describe it, X, which is our unknown variable in math. And the name kind of stuck over the years, X-rays. People like Marie Curie and other people were studying X-rays. And before we understood how dangerous this form of radiation was, some studies were done. But these scientists, when they were actually trying to study X-rays, they found out too late that X-rays can cause all kinds of issues with our body. Now, don't be afraid though. When you go to the dentist, when you go to the doctor and you get an X-ray, you're exposed to X-rays in such low dosages that it's perfectly safe to go and get your arm X-rayed to make sure you have no broken bones. Now, the reason why X-rays work to detect the bones inside of our body is because this type of electromagnetic radiation easily pierces tissue, but it doesn't pierce the denser bone. So while the X-ray pierces our tissue, it reflects off of our bones back into the X-ray camera. And that's how we could use X-rays to see our skeleton using this portion of the electromagnetic spectrum, which is pretty cool. And beyond X-rays, we get to the most dangerous form of electromagnetic radiation, which is gamma rays. Gamma rays is high energy light, the lowest wavelength, highest frequency, and gamma rays are one of the biggest dangers of space travel, believe it or not. Gamma rays are flying around our universe all the time. And we need some way, if we're going to be doing interplanetary space travel, we need some way to protect our astronauts from this gamma ray radiation. Now, hopefully that quick summary of all these different types of radiation kind of gives some character to each portion of the electromagnetic spectrum. This is all of the different light inside of our universe, and depending on where you live, what frequency and wavelength you have, it characterizes what type of light we're looking at. Now, no matter where you live in the electromagnetic spectrum, no matter what light we're looking at, all of that light travels at the speed of light. We discussed this before, but the speed of light is the universal speed limit. Nothing can go faster than the speed of light inside of a vacuum. And the reason why we have to specify this, that traveling in a vacuum, because that's where light travels the fastest. If we have light traveling through any type of materials, light does actually slow down, and that's something we're going to be looking at in a future lesson. But inside of a vacuum, light travels at the speed of light, which is 3.0 times 10 to the 8 meters per second. We use lowercase c to denote the speed of light in a vacuum. There's a few different ideas of why we use c to denote the speed of light. Some say because it's a constant, right? So lowercase c for constant, speed of light in a vacuum. It could also come from the Latin word for light, which I don't remember off the top of my head, but we use lowercase c to denote the speed of light in a vacuum. And because it's a constant, we could find this on our reference table at page 1. Okay, so light can be modeled as an electromagnetic wave, which means it could follow the same formula we've been using throughout our study of waves. We've been using V equals F lambda, which V denotes the speed of the wave. Now, if we're inside of a vacuum and we're looking at an electromagnetic wave, we can say that C is equal to F lambda. And we get C out of our reference table. And if we know something about the frequency of that light, we know something about the wavelength of that light. And we can always solve for one or the other as long as that light is moving through a vacuum. If we have two of the variables, we could solve for the third variable. Okay, so we're at a point where we could start solving some questions looking at our electromagnetic spectrum. Let's try 2 examples and then we'll finish up our video for today. Okay, example 1. We have an electromagnetic AM band radio wave, and this type of radio wave could have a wavelength of what? Does it have a wavelength of 5 millimeters, 5 meters, 500 meters, or 5 million meters? So how do we start to answer this question? Well, if we look at our electromagnetic spectrum, again, you find this in your reference table if it's not given to you right underneath the question like it is here. We can find AM radio waves inside of our diagram. Any electromagnetic waves that exist in this little range would be AM radio waves. And we can look. Wavelengths are given on the top of this diagram. And AM radio waves live somewhere between an order of magnitude of 2 and an order of magnitude of 3. So that means that if we're looking, we have like a significant digit of 5 here. That means it can live somewhere between 500 and 5,000 meters as a wavelength. So then the best answer here would be choice 3. Now this is pretty wild to think about. 500 meters. That would equate to like 1,500 feet. That's almost 2 football fields. 600 meters or 600 yards would be about 2 football fields. And that's the wavelength of this electromagnetic radiation. So if we tracked any 2 points in phase, we're looking at over a football field of the distance between any 2 points in phase or the wavelength of this electromagnetic wave. It's pretty wild. So the correct answer here is choice C. All right, this question's a little trickier. There's a few steps here, so make sure you follow along. Which color of light has a wavelength of 5.0 times 10 to the negative 7th meter in air? So we have blue, green, orange, or violet. Okay, so we're looking at electromagnetic spectrum. Now, if you look closely, the visible light here is only given in terms of frequency, not wavelength, right? Because all of these numbers down here correspond to the frequency of the visible light, not the wavelength. Okay, so how can we figure this out based solely on this diagram? Well, we know that we could calculate the frequency if we know the wavelength. Now, it says that this light wave is traveling through air. Air is very close to a vacuum. The molecules are very dispersed. So while light does slow down a bit in air, it does pretty much act like a vacuum. So we can use this equation here. C is equal to F lambda. And looking at a reference table, we can see that the speed of light is 3.0 times 10 to the 8th meters per second. Okay, and that's equal to F multiplied by lambda, which is the wavelength, and the wavelength here is 5.0 times 10, I'm running out of room, to the minus 7th meters. Okay, so we could use that to solve for the frequency. And when we solve for the frequency, 3.0 times 10 to the 8 divided by 5 times 10 to the minus 7 works out to be 6 times 10 to the 14th hertz. Now you might be asking, Mr. Hatzfeld, 6.6 times 10 to the 14th? That doesn't tell me what color this light is. But if we know that it's 6.0-ish times 10 to the 14th hertz, we can look at our electromagnetic spectrum and we see that 6 times 10 to the 14th hertz lives between these two boundaries, between 5.2 times 10 to the 14th and 6.1 times 10 to the 14th. So the correct answer here is choice B, which is green. Green has a wavelength of 5.0 times 10 to the minus 7th meters in air. Now this is pretty interesting because it gives aesthetic properties like color, it gives them quantities, right? We now can talk about green as the fact that it's somewhere between 5.2 times 10 to the 14th hertz and 6.1 times 10 to the 14th hertz. And understanding the science behind the aesthetics is one of the coolest things that I find in physics. The fact that we can quantify, predict, and use science to determine things like color, I find to be pretty interesting. Okay, so I hope you found this video useful. We'll be looking at some other aspects of light, of optics in future videos. Hope everyone's doing well, and I'll see you next time.